This video is for Math 0242-1342, and we're going to be starting Chapter 6 and doing 6.1, 6.2, and 6.3 here in this video. A total of 15 problems. I think there's 5 from each of the 3 sections. So even though this first problem comes from something we did back in Chapter 1, there's a reason why they're including it again here. So it says, describe if this variable is discrete or continuous. If you remember back in Chapter 1, we would break data into a flowchart of either qualitative or quantitative. Qualitative are things that are neither counted or measured. Usually words, but sometimes numbers like people's names or phone numbers are qualitative. Quantitative is when you can either count or measure them. There's math going on, and that's because it's counting or measuring. There's 2 of these, discrete or continuous. Discrete are things that you count. Continuous are things that you measure. And sometimes it's hard to tell that, like I think I gave the example of running a 100-meter dash in the Olympics. As the time goes by, 1, 2, 3, 4, it sounds like you're counting that, but time is a measurement. And another way to tell is if you think of 2 close examples, like I can run the 100 meters in 10 seconds or I can run it in 11. If it's only 10 or only 11 and nothing in between is possible, that's discrete. Like number of students in a classroom, I can have 30 students or 31. I can't have 30 and a half even if I want to. But in time, not only is it a measurement, but it doesn't have to be exactly 10 or exactly 11. It could literally be 10 and a half or 10.34 if I get a more accurate measuring device. So if it's possible to get more and more accurate, that's continuous. Now in this chapter, the reason it's important is we're going to make a chart called a probability distribution. And it has 3 rules to be a legitimate chart. The first rule is that the X column, the very first column, has to be discrete. So if you get something that's continuous, then in this chapter, you can't make a chart for it. So here's exactly what I was talking about. The amount of time you wait at a bus stop is continuous because time is a measurement. And it could be 10 minutes, it could be 11 minutes, but it could be 10 and a half. It's probably unlikely to be exactly 10 or exactly 11. And then in Chapter 6, if you were making one of these probability distributions we're about to make here in a second, you wouldn't be able to do it for time waiting at a bus stop because that's continuous. Now if I try another one, maybe I get discrete this time. Weight of a randomly chosen college student, weight is another measurement, so that's continuous. Try another. Time is continuous. Maybe this one's always continuous no matter how many times I try it. So the number 2, the different one? No, okay. See, this is a probability distribution here, but let me try one last time, see if I can get a discrete one. Final exam score. See, final exam score of a random student. Most tests give you scores that are integers only. You can get a 99 on the test, or you can get 100. I guess in theory, a teacher could say you got 99 and a half, but usually test scores are to the integer. And it's either 99 or 100 and nothing in between. If so, then it's discrete. And then if that's discrete, like they said here, it's good, then you could make a chart for it. So at least I got one discrete by doing that 4 times. But here's the chart. The first column is X, which has to be discrete. Maybe these are test scores here, 55, 65, 75, 85. The second column is for probability. Now we already learned in a previous chapter, in chapter 5, probability answers are always between 0 and 1 no matter what. They literally cannot be negative and they can't be bigger than 1. I have a probability right here in this chart that's listed as a negative. That's a mistake. Probability can't be negative or bigger than 1 if you look at it individually. So they have these first couple of problems where they ask you, is this a legitimate probability distribution or not? This table does not represent a discrete probability distribution. because probability cannot be negative. So all probabilities have to be between 0 and 1. The probabilities add up to 1, but all probabilities are not between 0 and 1. So they're actually doing both Rule 2 and Rule 3 here at the same time. Rule 1 is you have to have discrete data in the first column. They often don't tell me what x is here. It doesn't say what x is about. So I don't have to worry about Rule 1 on this problem. I guess they covered it by doing that discrete or continuous problem on the previous one. So I can't tell if x is discrete, but at least possibly it could be discrete because they're only listing integers here. Then each individual probability has to be between 0 and 1. It can't be negative, can't be bigger than 1. I have one that's not. So that makes this fail right then. And then the third rule is if you add all the probabilities up, it's supposed to equal 1 exactly. And even if you use this negative 1 that wasn't supposed to be here, this negative 0.1. Let me clear this. Negative 1, there's not supposed to, well, 0.1, sorry. Negative 0.1. There wasn't supposed to be a negative. But there is one. So what if I just put it as is and then add all the rest of them? This adds up to 1 because the negative 0.1 and the positive 0.1 cancel out. So that's Rule 3, that if you have a legitimate probability distribution, all the probabilities are supposed to add up to 1. So technically this one meets Rule 3, Condition 3. But Rule 2 is failing. And it only takes one rule to fail, and then you would stop. So if you didn't have discrete data, if you had continuous, then there's no point in going forward. If you have any illegitimate probabilities that are bigger than 1 or negative, you stop. Or if the sum of all the probabilities isn't 1, you should stop. And you could have 2 or 3 of these rules violated at the same time, in theory, if they're just testing your knowledge. But if you find one that fails, it's a little bit pointless to keep checking the other rules, except for just the practice of it. Okay, so this one now we don't care if it's legitimate or not because they're not going to give you an illegitimate probability distribution if they want you to find the mean and the standard deviation of it. Okay, so x's can be negative actually, so don't let that bother you. Probability can't be negative, but x can be negative. In fact, they often use these charts in gambling games. If you go to a casino where they play a gambling game, every gambling game in Las Vegas has a probability distribution behind it. And they make sure that the mean is negative for players so that in the long run the casino wins. And every game has points where you win or lose money. So because x has to be discrete and money is discrete because you count money, this can represent losing money in a gambling game if you put negatives on the x variables. So x's can be negative. Probabilities have to be between 0 and 1, and notice they all are. They're all 0 point something. None of them are negative. None of them are bigger than 1. And if I add them all up, it's supposed to equal 1 exactly. So I'm actually double checking if this is a legitimate one, even though I don't have to, because they shouldn't give me one that's illegitimate if they want the mean and standard deviation of it. But just to review what happened in number 2, this one should work. All 3 things should be good here. See, it adds up to 1. The sum of all probabilities 1. Each individual probability is between 0 and 1, and x's could be discrete here. I don't know what this is about, but they could be. So if you're going to find the mean, I'm going to show you this both the slow way and the short way. If you write this down or have somewhere where it's already written down for you, the first 2 columns have to be given to you. So I'm just rewriting what was already given to me. Negative 10, negative 9, 2, 4, and 8. Turns out the mean is pretty easy to do even by hand. In fact, they sometimes have junior high kids do something similar. They wouldn't work in decimals, but they would do something similar to this. So the probabilities are in decimals, 0.12, 0.24. 0.15, 0.23. and 0.26. So we make a third column, and in the third column you literally do x times the probability of x. You could do this with a plain calculator, just literally -10 times 0.12 is -1.2. Then I want to do -9 times 0.24, -2.16. 2 times 0.15. 0.30, 0.3 or 0.30. 4 times 0.23, 0.92. And finally, 8 times 0.26. 2.08. The mean is the sum of all these decimals right here. If you multiply straight across and add them all up, that's the mean. So I'll do it from bottom to top because I still have this 2.08 in my calculator. So I'm going to add 0.92, add 0.3, and then add a negative or just subtract 2.16 and subtract 1.2. This adds up to -0.06. See, every gambling game in Las Vegas makes sure that this adds up to negative. If this adds up to negative, then the player loses money in the long run. They lose 6 cents every time the game is played. So the mean is -0.06. It's like losing 6 cents every time the game's played. Now, you can also do it more easily here if you want to. I can go to Stat, and while it's on Edit, press Enter. Put all these x's in L1, -10, -9, 2, 4, and 8. Then you go over to L2 and put the probabilities. 0.12, 0.24, 0.12, 0.24, 0.15, 23, and 26. 15, 23, and 26. 23, 26. Okay, if you got your L1s in, you got your L2s in, there's an L3 right here, list 3. Right arrow to go to list 3. But notice the cursor is waiting for me to type something. You need to up arrow so the L3 name is actually highlighted. Not the first entry, but where the L3 name is. If you press second and the number 1, that tells it L1. See how it says L1 right there? Times second and the number 2 is L2. I'm doing every L1 times every L2 number. Press enter, does all 5 of them for you that quick. That was much faster than I did them by plain old calculator. And worst come to worst, you could write all these L3 numbers down and add them up yourself if you needed to. The sum of the L3 numbers is the mean. You can even do it in the calculator quickly, and I'll put the steps down here in a second, but it's second mode quits the screen. You want to quit the screen because if you give it the command in there, then it'll place it in the next available slot, and then it could delete over old data or add something in that shouldn't be there. So second mode quits the screen. Now we press stat to go into that spreadsheet, but now you want to press second stat. Not regular stat, but second stat. Right arrow over to where it says math. Now there is an option to do mean, but that won't work here because we have 2 sets of data. So you don't want to pick mean, you want to pick the sum. I want to add up that third list. So pick number 5, the sum, and then tell it L3 by hitting second and the number 3. And when I press enter, this should say negative 0.06. See? So you can choose to do that too. The only thing is you'd have to remember what buttons to push. But when you want to add up a list, what you do is you press second mode. That quits the screen. Second mode is quit. This gets you out of the spreadsheet. Then you want to press second stat. Right arrow twice over to math. Choose number 5, the sum. Press enter. And you'll be back on the main screen. It'll say sum parenthesis because it doesn't know what you want it to sum up. So then you have to type in L3 yourself and press enter. You don't even have to close the parenthesis if you just press enter right then. Press enter and the mean pops out. The mean or the average is the result of that. So this is a quicker way of doing it. If you can't remember these buttons to push, you can always do it the slow way too. Excuse me. And then you can get the mean right. Most people get the mean right on tests. It's not that hard to do. The standard deviation takes a while. Remember when we did standard deviation in chapter 3? It's similar here, how you got to do a number of steps to get it. I want to look up something real quick here. I'm going to send you a formula packet, and right now all you need is page 1 on it. This is page 1 of 11 of a formula packet. And there's nothing on it that's helpful till you get to chapter 4, which this is a different book, but this book's chapter 4 is your chapter 5, where there's all these probability formulas. Now, I did a lot of the homework without using any of these, but at least they're on there. We're now doing probability distributions. Our chapter 6 is their chapter 5. So right here, the very first formula on here is what I literally just did right here. Here's the mean of a probability distribution. It's the sum of that little, that's a Greek sigma, capital sigma, sum of x times the probability of x. That's the mean. And then the standard deviation of a probability distribution is this formula right here. So I have to do x squared times probability, sum them all up, and then minus the mean squared and take the square root. This is the manual way to do it. So the formula says, where's my whiteboard? Here it is. Okay, so we're going to take a square root of the sum Okay, square root of a sum, it's x squared times probability of x. And then you minus the mean that you just got squared. So this is the symbol for mean. And that was negative 0.06. So we just got part 1 answer. Okay, so we got an x column. I did the x's in L1. Go back into stat and edit. L1, those are the x's. So what if I use L4, go to the top and hit L1 squared? There's all the x squareds. The formula says I'm supposed to do x squared times probability of x. Well, probability of x is back here in L2. So what if I take each L4 times each L2, and I can do that in L5 if I go up to the top? L4 times L2. Whoops. L4 times L2. That's each x squared times each probability. And you sum that up, just like we did for the mean. If we sum up L5, that's this result here. So second mode to quit the screen, Second stat, math, if I do the sum of L5, 52.36. That's this right here, 52.36. This was the sum of x squared times probability of x. Now, anything squared is positive, so if you do a negative 0.6 times a negative 0.6, it'll be positive whatever. So negative 0.06 times negative 0.06, this is what a square literally means. The same thing times itself. The issue is if you type negative 0.06 and square it, this calculator is so smart that it literally does what you're telling it, not what you mean for it to do. It's only going to square the 0.06, and then it'll just carry the negative along. It seems to say that the answer is negative, even though it's not. So technically, you need a parenthesis around your negative 0.06. Square that, and that's how you get this positive 0.36. So it's 52.36 minus this minus. Don't try to change this double negative to a plus, because the second negative gets squared and turns into a positive. And becomes, did I do it here? No. But see, if I hit squared here, it correctly makes it 0.0036. Some calculators do it correctly, but others will literally follow the order of operations. So 52.36 minus 0.0036, and then you square root this. In fact, this would be the variance. Sometimes they ask for that too. But if I square root 52.3564, the standard deviation should be, let's see how far they want it rounded. It's usually a long, messy decimal, so round the answer to 3 decimal places. 7.236. You got to bump this 5 up to a 6 because there's a 7 after it. 7.236. Okay, see, that was correct. And then there's an even easier way to do it if you have a TI-83 or 84, which I do here. So all you need is to put the data in L1 and L2. The original data goes in L1 and L2. I could have skipped doing all these other steps. If you go to Stat, Calc, 1var stats. Now, 1var stats is meant for one list of data, so if I press enter right now, it'll only do the L1s. But if I tell it L1 comma L2, it combines them. And the mean should be negative 0.06, and the standard deviation was 7.236. See, there's the mean of negative 0.06, and there's the standard deviation of 7.236. So you could do that too if you wanted. And I know that this calculator is about 10 years old, so when I go to Stat, Calc, 1var stats, it takes me right back to the main screen right away. And I can type L1 comma L2 and get these two answers to spit out right away. I've been getting students over the last handful of years showing up to class, and they have, I guess, what you would call like a 2.0 or a 3.0 version of these calculators. They must be making upgraded versions of them and adding features to them that these older ones don't have. Because I literally get 2 people with a TI-83 Plus. This one's a TI-83 Plus. And I get people with TI-83 Plus, and some have the extra features and some don't. So I think it's based on the year that the calculator was made. This version was made about 10 years ago. So if you buy a newer one in a store right now, yours will probably be able to do more than this one can do. But one thing that they improved in it is they have separate screens you go to. If you choose one var stats and it takes you to a separate screen, if it doesn't take you back to the main screen, you go to a separate screen. It's just a little more user-friendly, and it tells you what you need to be plugging in. And you'll see this, I'll have to explain this more when we get further into this textbook, because it happens in future chapters too. So these older calculators, I call them the typers because we're typing on the main screen. And on the newer ones, there's a little paste at the bottom of the separate screen you go to. So I call those ones pasting calculators. And I discovered when somebody showed up to class with one of these, I didn't even know they did this until somebody showed me their calculator. And it turns out in there, when you go into this one var stats into a separate screen for one var stats, there's a spot where it says list, but it won't let you type L1 comma L2. It won't let you put the comma. So just leave it as L1. I think it defaults to L1. Leave it as L1 and go ahead and hit paste or calculate or whatever it says at the bottom. And you'll get the wrong numbers. But it's okay if you just do it wrong on purpose at first. Run the one var stats, and if you can't type L1 comma L2, just leave it as L1 and press calculate or enter or whatever. And you'll notice your answers are different than mine. But as soon as you do that, then you can hit second enter. Second enter on the main screen calls up the last thing you told it to do. And yours will say one var stats of L1 only because it only lets you do L1 there. But right now, then you can type the comma L2. Comma's right above 7. Comma L2, and then if you run it a second time, then you'll finally get the answers right. So even if you have the newer ones that don't let you do it inside the screen, you can still trick your calculator, I guess, by getting it wrong at first and then hit second enter and it'll let you do it at that point. So let me just try another real quick here. Here's the shortest way to do this in total. If I'm doing a mean and standard deviation of a probability distribution, I only need list 1 and list 2. So go to the top of each list 1 and list 2 all the way at the top and hit clear enter. You don't have to clear the other lists out, just these two. And in L1, I need to put -6, -2, 2, 4, 6 in this second example. Then go over to L2 and put 0.17, 0.07, 0.24, 0.28, 0.24. So I put all the x's and probabilities in there. L1 and L2 only. So then hit stat calc one var stats. Notice I'm back on the main screen. You might be in a separate user-friendly screen. And then there's a part where it says list, and I think L1's there already. So mine lets me type L1 comma L2. Yours probably doesn't in the screen you're in. But just leave it as L1, go down and hit calculate and get the answers wrong. Your answer should be different than mine. But then if you immediately hit second enter, yours will only say, you'll only see this actually. Yours will say one var stats of L1 only, which is why your answers are wrong. Yours is only doing L1, but it needs to do both. So comma L2, you can type it now. And now you get the same answers as me. 1.88 is the mean. The top one's the mean. This happened to be the same thing, but the mean is X bar here. And then the sigma is the standard deviation. So 1.88 and 4.117. Bump that up to a 7. 4.117. And this was 1.88. So then this problem can be really easy if you do that. Or you could do it the slow and slow way if you don't have a graphing calculator. Okay, here's a short problem. Remember how there is 3 rules about a probability distribution. Now, I like to write them vertically like this, too. I usually write mine vertically, but you can write them horizontally and have x go across the top and probability go underneath it. That's fine. X's have to be discrete. I don't know what this is about, so I can't tell that, but 6, 7, 8, 9 could be discrete. Probabilities have to be between 0 and 1, no negatives, nothing bigger than 1, and none of them are. There's a 0.2, a 0.3, and a 0.1. And then the sum of all of them has to equal 1. So they can do this to you, and they can leave one of them blank and ask you, what's the missing one? Well, if you add up the other ones, 0.2 plus 0.3 plus 0.1, I only have 0.6 of it so far. So what am I missing to get up to 1? Just do 1 minus whatever you add up to, and that's what you're missing. I'm missing 0.4 of this to make it add up to 1. So you can find one missing value if you do 1 minus all the other ones. Or after you have a probability distribution, you can answer short questions like this. Find the probability that x equals 2 is what this is really asking. So come to when x is 2, and the probability is right there below at 0.3. That's what this is really used for. So say this is a gambling game where you win $0 or win 1 or win 2 or win 3 or win 4. So this is saying you'll win $2 0.3 or 30% of the time. What's the chance I get less than or equal to $3 in some gambling game, for example? Less than or equal to 3, that's all of them except for the 4. Less than or equal to 3 is 3, 2, 1, and 0. So add 0.1 plus 0.3 plus 0.2 plus 0.3, which is 0.4, 5, 6, 7, 8, 9, 0.9. Find the probability that all 4 tires have low air pressure. So that's this 4 right here, 0.1. I guess this is about how many tires on a car have low air pressure. So you come out in the morning and sometimes one tire is low, but what if all 4 are low? 0.1% of the time all 4 tires are low. Find the probability that no tires have low pressure. That's when x is 0, so 0.3. So this is where you can use a probability distribution to answer short probability questions. Okay. This is the same thing really that we did a couple of problems ago. Compute the mean, and another symbol for it is mu with a little x subscript. I'll do this the short way again. If you have to do it the long way, that's fine, but it's nice when you can do this the short way. Stat, edit, just clear out list 1 and list 2. Type 0 through 4 in list 1. 0, enter, 1, enter, 2, enter, 3, enter, 4, enter. Go over to L2 and put 0.1, 0.3, 0.3, 0.2, 0.1 for the last 3. Stat. Calculate 1 var stats. Get it wrong first if need be, and then hit second enter and type L1, L2. The mean is 1.9. All they want you to know here is that this is the symbol for mean of a probability distribution, 1.9. The standard deviation is this sigma value, which is right there. See how they write it here too, sigma x, sigma x. How many decimals? 3, yep. 1.135, but there's a 7 after that, so make it 1.136. So this is, number 6 is exactly like 3. They just want you to know that those are the symbols, I guess is why they put this one again. And just more practice of doing that. Okay, so I was wrong. I thought there was 5 problems from every section, but actually there were 6 problems from section 6.1. So now we're into 6.2. 6.2 is a completely different topic, and it's a better one actually. This is the most important thing about chapter 5. I'm sorry, chapter 6. I'm used to this being chapter 5 actually. So binomial is a special type of probability distribution. We just did very generic ones for that whole section there. Binomial is a very specific one. And if you get a binomial, it's a little bit easier to work with. But not everything's binomial. First of all, in its name, bi means two. Like bicycle has two wheels, bifocals have two lenses. There can be only two outcomes if you want to have a binomial. The classic example is flipping a coin. Heads or tails is all that can happen. That's two outcomes. If you roll a die and try to get a 1, 2, 3, 4, 5, or 6, that's not binomial because now you have 6 outcomes. Now, sometimes you can take something that's not binomial and turn it into binomial. Instead of trying to roll a 1, 2, 3, 4, 5, or 6, what if I try to roll a 3 or not a 3? Now it could be binomial. Or you could try to do evens versus odds. That could be binomial. Now, just because you have two outcomes doesn't make it binomial because there's still a few more conditions. You need to have a set number of trials. Like flip a coin 10 times. You know ahead of time you're going to do it 10 times. That's a set number of trials. Another one that's close to binomial that's not binomial is when they say flip a coin, and people hear that, oh, it must be binomial, I'm flipping a coin. But they say flip a coin until the heads comes up for the first time. The problem with that is you don't know how long it's going to take. It might happen the first time, it might take 5 tries, it might take 2 tries, it might take 10 tries. It maybe never happen, maybe just keep flipping tails forever. If there's no set number of trials, they can't be a binomial no matter what. And then there also needs to be the same probability of success every time. At least coins come up heads 50% of the time, all the time. If the probabilities are changing for whatever reason, then it can't be binomial either. So there are 3 main variables here. N is the sample size or the set number of trials. How many times are you going to do your experiment? P is the probability. And X is the number of successes you're hoping to get. Flip a coin 10 times, what's the probability of exactly 7 heads? If I flip a coin 10 times, the size of my experiment is 10, so that's N. Try to get 7 heads, that's X, 7. And then they usually tell you P in the paragraph, but sometimes it's obvious to them and they don't tell you. Flipping a coin, I guess they assume you would know that that's 50-50 heads or tails. So you don't just automatically assume you have a binomial. We have to make sure these conditions are true. 30 students are randomly chosen from a small college with an enrollment of 2,400. Let X be the number of students who are freshmen. Could this be a binomial? Well, you're either a freshman or you're not. You can't be a freshman and a senior at the same time, or you can't just show up to college and be nothing. So you're either a freshman or not. It's got 2 possible outcomes. The set number of trials, we're going to check 30 students to see if they're freshmen. And the probability of being a freshman, I don't see why that would change at any point. So this is a binomial. It meets the conditions here. This has a binomial distribution. The number of trials is the 30 students we're going to look into. And that's all they're asking for in this problem. They could have asked for the P as well, but they didn't. Or the N. Oh no, the X is the other thing they could have asked for. Okay, so now we're going to determine a probability for binomials. So you have 2 choices here. You can do this the slow manual way or the easier way with the calculator. N equals 9, P equals 0.3. There is a formula on the formula sheet that I'll send you. Where did I put it? Here it is. It's right here. This third thing down. So we already did the first 2. We did the mean of a probability distribution. We did the standard deviation of a probability distribution. The third one says binomial probabilities. and it looks like a fancy formula, but it's not as bad as it looks. There's what they're really doing is, let me show you the better way of thinking about it. So a binomial probability the probability that x equals, how did they write that? You're just writing probability of x get rid of the equals. Okay, it's n factorial over r factorial times n minus r factorial times the probability of r p to the r, and then let me do it exactly how it is on here. And q, that was what I wasn't sure if they put q or if they put 1 minus p. So q to the n minus r. This big messy fraction is literally NCR. That's the formula for combinations that we learned last video. So it's probably easier to think about it this way. So in the first part of number 8, they asked me to do the probability of 6. Given that n is 9 and p is 0.3. Every binomial, there's always an n and a p that they either just come right out and tell you, or it's easy to figure them out. N is 9, p is 0.3, and they want me to do the probability of 6, so that's the x. So if you do n combination x, 9 combination 3, p's 0.3, and the r here gets repeated there and up here. So once there's a 3 down here, there has to be a 3 up there no matter what. Now they never tell you q because they think you're supposed to know this by now. P and q are complements of each other. It's like rain and no rain. So if there's a 0.3 or 30% chance of rain, q is always 1 minus p. Because that's the complement. I ran out of room here, I can't write it, but 1 minus p. 1 minus 0.3 is 0.7. If you're going to do this with the calculator, the TI-83 or 84, you don't need to know q. But if you want to do this manually, you have to figure out q yourself. It's 0.7. And then you do n minus r, but that's these two numbers right here, 9 minus 3. And hopefully you can do 9 minus 3 in your head and say that that's 6, or if you can't, do it in the calculator first. So remember how to do a combination. 9 combination 3 means 9 times 8 times 7 over 3 times 2 times 1. So I'm going to do this entirely if you don't have a graphing calculator. 9 times 8 times 7 divided by 3 divided by 2 divided by 1. That's the combination. 84 times 0.3 to the third power. So raised to the third equals times 0.7 to the sixth power. Two, 6, 6, 8. They usually like 4 decimals here, but I should check. Maybe they only want 3. 2, 6, 6, 8. See, 4 decimals. 2, 6, 6, 8. Let's see, 0.3. Oh, 9. Did I say 7? 9. 9 combination 3. Oh no, that's what I did wrong. It was supposed to be 9 combination 6. I don't know where I got this 3 from. This is 6, not 3. So this will be 9 minus 6, which equals 3. Okay, so 9 combination 6 is a little longer. Now I have to do 9 times 8, that's 2, times 7, that's 3, times 6 is 4, times 5 is 5, and times 4 is 6. Divided by 6 all the way down to 1. So this was 84 right here, times 0.3 raised to the 6th power, not 3rd power, equals times 0.7 to the 3rd power. 0201. Okay, so, or here's your other option. If they want you, if they tell you at number 8 that n is 9, p is 0.3, and then when it says find the probability of 6, that means x is 6. See, they don't give you q, and you can figure it out yourself if you need to. But if you want to do this in the calculator, you don't even need q. There's a function in the calculator called binom PDF, and you put n first, p second, and x last. You don't need q. And there's a difference between being a typer or a paster, as I was mentioning earlier. So if you have an older version of this calculator, like me, you're what I call a typer. So this is found under second vars, and I'll write this down, but it's second vars. Vars is short for variables. And if you up arrow, you'll get there faster because it's near the bottom. It's the 5th and 6th one from the bottom. So up arrow 6 times. 1, 2, 3, 4, 5, 6. There's a binom PDF and there's a binom CDF. We're going to get to CDF in a minute. You pick PDF when you're doing one case only. All I'm doing is the case of probability of 6 only. But if it was greater than 6 or less than 6, then I would use CDF. So I'm going to choose binom PDF, and I'm a typer, so I'm back on the main screen. So the typers, old people of us, we have to remember that it's N first, then P. Somebody's knocking on my door. And then X. And notice this should be the same answer that was 0201. See there? See, 0210. I think that's what we got right here. Oh no, I had 01. Okay, it's off a little bit. Okay, so but that's generally what you do on those. So N was 9. Let me make sure I typed it in right. N was 9, P was 0.3, and 6, yes. So again, the other way was 9 combination 6 times 0.3 raised to the 6th power times 0.7 raised to the 3rd power. Yeah, okay, I must have typed that other one in wrong. And they took the answer somehow. I guess if you're close, they'll count it because it is off a little bit. 02, I got 0201 using my plain calculator, but it's more accurate. Oh no, I guess I just typed it wrong. I had a dyslexic moment and I put 0201, and they took the answer somehow. Usually they count that wrong when you're off a little bit like that. So it did agree. It was the same by hand and by calculator. So that's your choice. If you have a TI-83 or 84, you can do a binom PDF or CDF. Then you don't need this formula for it. Where'd the formula go? Right here. So you only need this third form if you want to do these binomials by hand. Now the part B and the part C, these formulas are good here. If you want the mean of a binomial, it's literally n times p. You don't have to go through all that long stuff of the generic ones. Whoops, I was right there. Part 2 says find the mean. It's literally n times p. You could do that on any calculator. That's the two things they give you. N times p is 9 times 0.3. It's 2.7. So means and standard deviations of binomials are very easy. They're harder for those generic ones. Now they want the variance and the standard deviation. So the mean is n times p. The variance is n times p times q. And then the standard deviation, as always, is the square root of that. So if we do n times p, and they never tell you q, but q is 1 minus p, so 1 minus 0.3 is 0.7. The variance would be 1.89. And then if you square root that, you'll get the standard deviation. And they want 2 decimals, so 1.37. So those are on the formula sheet that I'll send you. That's weird. Oh, I know what happened. I did the square root of the whole thing, but let me clear this. When I got, or maybe I didn't have that long of a thing. What did I have? I had 9 times 0.3 times 0.7. Oh, it was exactly 1.89. That is weird. So let me clear this. 1.89. Oh, you got to hit that first and then square root. 1.37 round to 2 decimals. Oh, no, I misread it. See? Round the variance to 2, standard deviation to 3. So they're kind of wrong because I didn't do 3. And there's a 4 after that, but then there's a 7 after that, so you got to add 1 to that 4 and make it a 5. Okay, now it's correct. Okay, see, here's this where they want you to learn this stuff, but before we do that, I better do a whole problem. Yeah, here's a good one. Okay, so I'll go back to 9, but here's this is what the essence of the chapter is about right here on this number 10. A student takes a multiple choice test that has 7 questions. That's your set number of trials right there. So n equals 7. I know I'm going to check 7 questions. The student guesses randomly at each answer, and there's, does it say how many choices there are? No. Multiple choice test. Oh, there it is. Each question has 5 choices. So usually they come and tell you what P is as a percentage, but here they're making you use your chapter 5 knowledge. This is basic probability. If you're going to guess a multiple choice question with 5 choices, you have a 1 out of 5 chance to get that right, which is 0.2. 1 divided by 5 is 0.2. So normally they would have come out and said, oh, there's a 20% chance of getting it right, and then you would change it to 0.20, but this is another way they do it sometimes. Like with flipping a coin, they might not tell you it's 50%. They think you'll know that. So there's 0.2. And then if I need the mean, I would get Q. If I need the standard deviation, I would get Q and just do 1 minus P, but we don't need that here. So part 1 wants the probability of just 4. All they have is a 4 there. Part 1 is probability of 4. So that means X equals 4. Only 4, too. So when you're only doing one case, this is binom PDF. You only do PDF when you're doing one case at a time. And then typers have to remember to put the N first, the P goes second, and the X goes last. I have to remember this order, NPX. But if you go to, I told you I was going to write this down, second vars, you want to go to second vars, and then up arrow 6 times. Second vars, up arrow 6 times. When I press enter right now, it takes me back to the main screen. I'm a typer. I have to remember the order. All these newer calculators, they have this user-friendly separate screen that it takes you to, what I call a pasting screen. And yours, it reminds you of the order. What you'll see is it'll say trials first, and then you put a 9 there. Oh, actually, that was the last problem. Trials here are 7. So you have to put 7 first, and you don't put a comma. I don't think it'll even let you put a comma, but comma, I have to put the comma. And then it says P, put 0.2 for that. And then just down arrow, I have to put a comma, but you down arrow. And then we want to get exactly 4 of these right, so then put a 4. And yours just says X. So yours says trials, put a 7, down arrow, P, put a 0.2, down arrow, and then X, down arrow with a 4. And then you down arrow and hit paste. That's why I call them pasters. Press paste, press enter on paste, and you'll be right where I am. It'll take you to this, and it'll put the commas in there for you. Then you press enter and get the answer right. So 0286, unless they want me to round up to 0287, 4 decimals, yeah, 0287. Okay, so that's how you do just one case. Now they want me to do more than 2. More than 2, this is not a PDF. Part 2, I want more than 2. This is where it gets really painful to do these if you don't have a TI-83 or 84. So the N is 7 here, so I have to get somewhere between 0 and 7 no matter what. More than 2 does not include 2, but it does mean 3 or higher. So it turns out you can't do 3 or higher. You always have to go down to 0. So circle what the question's asking for, 3 or higher, and then I have to do the opposite of that and go down to 0. That's how the calculator was built to. It could only go down to 0. If it's going the wrong way and you have to turn around and go the other way just so you can go down to 0, then you put 1 minus, and these are all binomes. You only put PDF when it's just 4, but as soon as it's any kind of inequality, you put CDF. C stands for cumulative. And then the good news is you never change the 7 or the 0.2. The last number is sometimes the one in the question, and sometimes it's different than that number by 1. It doesn't matter whether this is a 2 or not. You want to look down here. I'm doing 2 or less, so that's why I put a 2 here. So I can type 1 minus, and you can too, even if you're a paster, second vars, up arrow to binom CDF, the 5th one from the bottom. I'm a typer, so I have to put 7.2 and 2, but pasters just put all 3 of them in, down arrow, and press paste. Then press enter again to get this answer, 1480. Okay, I'm going to go back to 9, but we need to learn more cases. This is a very typical binomial problem where they tell you the P is a percentage, 86%, and then the sample of 12, that's N. They always have the N and the P one way or another in the paragraph. But N needs to be first when we do this in the calculator. So 11 told me 86%. That's definitely P, but change it to a decimal, 0.86. And then N was 12. Part 1 wants, find the probability that all 12 were on time. So in other words, just 12. So this is where the X is only 12. That's the easiest case. This is binom, PDF. There's nothing tricky to a PDF. The N goes first, the P goes second, and the X goes last. Second vars, up arrow to binom PDF, 12.86 and 12. If you try 12 times, you can succeed all 12. 1636, but there's a 7 after that, so 1637. 1637. Find the probability that exactly 10. That's another easy one. Exactly 10. That's exactly the same as this. I can hit second enter and just change the 12 to a 10. I want exactly 10 this time instead of exactly 12. It's another PDF. 2863. 2863. Find the probability that 10 or more. See, this is different than the other one we did. 10 or more. The other one, remember that other one said more than 2. This is 10 or more. Not more than 10, but 10 or more. 10 or more. Well, this is definitely a CDF. As soon as you do inequalities, it's CDF. And if I go 0, 1, 2, 9, 10, 11, 12. More than 2 was 3 and higher, but 10 or more is 10 or higher. This actually includes 10. But I can't go that direction, so it needs to be 1 minus binom CDF. And of course, the 12 and the 0.86 aren't going to change. But notice this time when it says 10 or more, I have to do 9 or less in order to get the exact opposite. 9 or less, not 10. You don't always put the number in the question at the end. So this is 1 minus binom CDF, 12, 86, and 9. 1 minus second vars. Go up to the CDF option. 12, 0.86, and 9, not 10. 7696, there's an 8 after that, so make it 7697. 7697. And then it says, using a cutoff of 0.05, would it be unusual for 11 or more flights to be on time? So 11 or more is just like 10 or more. I can redo what I just did, but change that last number to 1 higher, make that a 10. Since 11 or more, the opposite of that is 10 and down. When you calculate a probability, if it's smaller than 0.05, if it's smaller than 5%, they consider that unusual. If the weatherman tells you there's a 4% chance of rain, and it rained, you'd be pretty surprised. But if they tell you there's a 48% chance of rain and it rains, it's not that you're expecting the rain, but if it rains, you wouldn't be surprised. So only if the probability is under 0.05 do we consider it unusual. Would it be unusual for 11 or more flights to be on time? No, it would not, because the probability is quite high, 0.48 whatever, 0.4834. So, well, that's what we use this for, is if we get less than 0.05, then it's considered unusual. So let me go back to 9 now. Here's where they have you, this is the calculator shortcuts. So if you get a 1 minus binom CDF, that's when it's going 1 higher than that actually. It's doing 6 and up. This is doing 6 and up or more than 5. This is more than 5, probability of more than 5 because it's actually 6 and up. But if you do binom CDF with a 5, that's 5 or less. If you do a CDF, it does that number and less. So this is 5 or fewer. That's what actually CDF is built to do. If you want to do, say you want to do between something. If I do a binom CDF with a 5 at the end, that's 5 or less. And if I do a binom CDF 2 at the end, that's 2 or less. So what this does is this does 3 through 5. If you ever needed 3 through 5, between 3 and 5, that's a way to do it. We usually don't get cases like that, but that's how you can do a between. And then if you do binom PDF with a 1 plus binomial PDF with a 2, see, if you don't have a graphing calculator, that's what you have to do, is you have to find every case you need and add them all together. So this is a case of 1 or 2. 1 or 2 would be this one. 1 or 2. So this is nice to learn the calculator shortcuts so you can do any of those. Okay, before I forget about it, let me give you the magic word of this chapter. We're into our 4th of 5 videos, so you should have 3, and they're all the same theme so far. So maybe you can guess what's coming next. This is going to be the Astros, Houston Astros, for video number 4, section 6.1 through 6.3. Okay, the last topic here, now we're into 6.3. Luckily, this is very similar, but a little bit different. There's another one besides binomial called Poisson. It's actually named after a French guy whose last name was Poisson, and that's actually the French word for fish. It would be like somebody whose last name is Fish. This is like N and P, but N and P, and then it's just different in Poisson. In Poisson, there is no set number of trials and there is no probability of success. What there is a lambda, which is the average number of successes per some unit of time, like 6, whatever. Find the indicated probability for a Poisson with a given lambda and t. Okay, round to 4 decimals. Probability of 3. Per 6. Okay, you have to get this lambda to be at the same units as the question, and I'm not sure what the question's doing here. So before I do this one, let me go to a more normal problem. Okay, see, this is better here, how it's worded like this. The number of potholes at a major street has a Poisson with a rate of 4 per mile. That's what I was looking for right there. 4 per mile. The question may or may not be about a mile. It can be, see how they changed this to 2 miles in the question here. X represents the number of potholes in a 2-mile stretch. So sometimes the number they quote you gets changed because the units change. In number 13, they started off by saying that lambda was 4 per mile. But then the question wants me to do per 2 miles. If the units double from 1 mile to 2 miles, then you have to double lambda to 8. And that's what number 12 is doing, but I need to look at it closer to tell what it originally was based off of. So now the rest you know how to do. The probability of 6, this part 1 wants probability of 6, which means exactly 6. So this is saying that x equals 6. So this is a PDF case, and Poissons can do PDF too. So Poisson PDF. Poissons only have 2 entry points. They just have lambda and x. There's no NPX, it's just lambda and x. And the x is clearly 6. Anytime it's PDF, that never is tricky. But sometimes this 4 goes here, but sometimes it gets adjusted first. So that's what I'm not sure about on 12. I think 12's getting adjusted, but I got to look at that closer. Poisson PDF 8, 6. And you do this exactly the same way. Second vars, up arrow, but stop on the 2 that say Poisson. Maybe you thought that said poison, but poison only has 1 S. This has 2 S's. Poisson PDF 8, 6. So 1221.1221. Or you can do more than 1. More than 1 means more than 1 means 2 and up, so I need to turn it around and do 1 and down. 1 minus Poisson CDF with the 8 first, and now I'm going to put a 1 last because I'm doing 1 and down. 1 minus Poisson CDF (8, 1). 9, 9, 70. You add 1 to this 69 and make it a 70. 9, 9, 70. And then between 7 and 9, inclusive means 7, 8, and 9. So really the only way to do that is to do a Poisson PDF. Do 7 first. Then repeat it for 8. Then repeat it for 9. This is what that one between problem was talking about on that number problem that I skipped, number 9, I think it was. So I did it for 7, I did it for 8, I did it for 9. You just have to add all these answers together. 1, 3, 9, 6, plus another, those happen to be the same somehow. 1, 3, 9, 6, both 7 and 8 had the same exact answer. And then 9 was 1, 2, 4, 1. 4033. 4033. When you're doing a between, you could, one way to do it. Another way to do it is I could have done a CDF with 9 and a CDF with 6 and subtracted them. Or if it's a small enough one, I can just do all of them and add them together. Okay, so number of potholes, 10 more minutes? Number of potholes is 4 per mile again, and now we're doing a 3-mile stretch of road. So you can do means and standard deviations of Poisson's too. Let me see if that's on the formula sheet. It's not, but it's easy actually. The mean of a Poisson is literally the lambda, but you just got to watch out if it's switched units. 4 per mile, they want it per 3 miles. So then you just got to multiply by 3. The mean would have been 4, but it got multiplied by 3, so it's 12. And then if you do the square root of that, that's the standard deviation. In Poisson, the mean is whatever lambda is, as long as you have the units right. And the standard deviation is always the square root of that, of the mean. And it says round to 4 decimals, 3.4641. They don't have this on the formula sheet, but it's easy to do. The mean of a Poisson is whatever lambda is in the correct units that you're doing, and the standard deviation is literally the square root of that. Usually you do the square root of the variance, but here it's the square root of the mean, strangely. Okay, this is a good problem. I think we got Poisson. There's a mean rate of 8 tweets per hour. So if they asked for the mean and it was per hour, the answer would be 8. If it was per 2 hours, it would be 16. And then if you want the standard deviation, just square root that. This, I don't think this is not about the mean, this is probability. So what is the probability that 4 tweets are received in a given hour? Notice this is a given hour and this is a given hour. So now they're not changing the units. Then I get to keep lambda as 8 the whole time. So what's the probability of 4 tweets in an hour? So in other words, exactly 4. And lambda is going to stay 8 this time. So Poisson PDF, 8 comma 4. 0573. Bump that 2 up to a 3. 0573. Now, here they're changing the units. What's the probability? There's 9 tweets in 1.25 hours. So I need to take this 8 and multiply it by 1.25. It's going to get bigger because of that. It's now 10. But we're still doing just 9 tweets, so that's another PDF. But you got to change lambda from 8 to 10. And then we're trying to get 9 tweets, so exactly 9, that's a PDF with 9. 1251. And then now we're going to a half hour, 1 half hour, so then we cut lambda in half. 8 per hour, well that means there would be 4 in a half hour, so now lambda's changing to 4. And we're trying to do fewer than 3, so that's a CDF case. Fewer than 3. Fewer than 3 doesn't include 3, but it is 2 or less. So then you don't need to put the 1 minus. You only put the 1 minus when it's going up. So this is Poisson CDF because it is an inequality. The lambda used to be 8 per hour, but now we're half hour, so we had to cut that in half. And then I'm doing 2 down to 0, so then you put a 2 here. Poisson CDF. Cut lambda in half to 4, and then fewer than 3 means 2 and down. And there's no 1 minus because I'm doing 2 and down. If it's already going down to 0, you don't put the 1 minus. 2381. This was a good problem to show how the units can change from part to part. So back to 12, I'm not sure if the units are changing here or not. The time is 6, but this 3, I don't know if that's based on 6 or not. So let me see what they're doing here. See, 9. Yeah, see, they're multiplying it by 9. Okay, now I see what's happening. So what this T represents is that's like saying that it's like 8 per hour, and that's like changing to 6 hours. So I didn't know what the T was, but the T means what you're multiplying lambda by. You're changing the lambda units by that much. So take the 1.7. Say it used to be 1.7 per hour. Now I want to do per 6 hours. So multiply by 6, and you'll get a new lambda of 10.2. But the 3 is easy because that means exactly 3. So that's a Poisson PDF. Poisson PDF, second vars, up arrow, Poisson PDF. The lambda changed to 10.2 because I had to multiply it by 6. And then I want exactly 3, so to keep that as a 3. And it's a PDF, that's the easier case. So I think it helped to do all those other ones first to understand what was going on here. 0066, 0066. Okay, so we got them all done. I got green checks on all 15 of them. Now you've learned what you need to know about Chapter 6. And this video contained all 15 problems from 6.1, 6.2, and 6.3. And we got all 15 right eventually. So now you can do any problem in Chapter 6. That's the end of this video.